Hello to viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about another continuation of topics, nuclear reality versus fantasy in 2025. I have a bad feeling I might have to do it annually now. So first you have to understand, there is a lot of love for people who do not dig too deep into it, and specifically engineers and scientists, because they do not have to worry about money, and their economic understanding is like, well, you will understand why every single project is so overrun. So reality is nuclear sounds like a silver bullet, meaning nuclear, all our problem gone. Now here's the deal. Why is that so? Well, it has zero pollution somehow. It has no intermittent output, meaning it's almost like a solar panel that just works. The end. Go home. So that is there. It has 24 into 7 into 365, meaning you just don't have to worry about it. Build it and forget about it. And there is no limit on the load also, because there is an inherent limitation. Right now, let's just say you have a solar panel. It has a limitation, like it cannot extract more than 1 kilowatt per square meter, and that's assuming 100% efficiency. You're not going to get that. So there is an upper limit to that. Wind also has something similar. So fundamentally, there are load limitation, meaning if you have very limited land surface area, you can't really do much. However, here you do not have to worry about those sort of things. So it's cheap, it's safe, it works anywhere, and this is so powerful in principle that it can decarbonize the whole grid today. Meaning, right now, why don't we decarbonize the grid? Well, here's the deal. 1 ton of steel, let's say, has X amount of price. Here's steel. If you increase its power consumption to reduce its carbon output, basically do certain electrolysis process that allows you to get a steel without carbon penalty, yeah, it can be done. Done. Science is sorted. You can just buy the machine to do it. It's just that now per ton steel cost will go at least 5x or even 10x. Here's steel. Nobody will buy that steel. So that creates the issue that we can decarbonize many of the polluting industries if you can provide power cheap enough. In principle, nuclear can do that. Now, here's the deal. How bonkersly high power that can be created, especially with fusion, is that enough energy to remove CO2 from air. Basically, you can just brute force remove CO2, and thankfully, you do not have to do it at site. You can do it anywhere. As long as you have powerful enough jet fans, you can suck enough CO2. And again, it would be better to do it next to power plant, but if you want to clean the whole planet, you can actually do it anywhere. As long as you have air circulation, you can just do it. Put it on a mountaintop and just suck out the carbon dioxide, and then cook off the oxygen from it and convert the carbon into coal, and then bury it back into the ground. Basically, press control Z. That's how much energy, in principle, nuclear has that. And again, NASA has been working on it. There has been resurgence of micronuclear reactors, and then you have the original dream, which is from basically Louis Strauss. That is, our children will enjoy in their homes electrical energy too cheap to meter. Now, the idea with too cheap to meter was like, bro, just take it. Like, we're gonna give you a fixed charge and take it. Like, of course, they have to do upkeep and maintenance, but they will not bother to meter it. It's like, bro, just take it. Like, power plants will, bigger industrial customer will be like, okay, take it. Like, that's how abundant power that can be. So it does feel like orgasm. It does feel like, do this, all your problem goes away. All of that. Like, I have seen way too many soldiers talking about it, engineers talking about it. It was like, do this, all problem solved. And that is not triggering a red alert in your brain. You have not studied well enough. So let's understand some history. Let's ground ourselves. And this is one thing that I do not like with basically Isaac Arthur, is that, like, fusion has not enough time. It's like, bro, it has. 2 December 1920, 1942, we achieved first fission chain reaction, meaning it was not only, oh, we achieved it. No. It was like, boom, boo. And again, that time we did not have enriched fuel, so they did not have to actually worry about runaway. But like, that was the like, oh, it's not something that can be done. Like, you can technically make a fission and fusion with a particle accelerator also. But the idea is achieving it as a like normal sustained process. That was done in 1942. And that was like, the door was open. And then we had the boom event that happened in 16 July 1945, the first boom event that was called Trinity, a big event. Then we had 27 June 1954, very soon, like 45 and 54, not that far away, and grid-connected nuclear reactor comes online in USSR, meaning it's not just, it's a thing that is selling electricity to the grid. That was quick, like, that was quick. That was like, damn. That was super duper quick. And again, it was super easy because all you had to do is yeet the coal furnace part with this reactor part. Everything else remained the same. So they were like, ta-da. So that happened. And The first time we went like this is fission domain. What if fusion happened? That happened on basically 1 November 1952. The first time we went a triple boom. Basically, we had a normal boom that compressed. That gave us fission. Fission compressed hydrogen. And you're like, okay, how the heck fission can compress it? Well, you have to understand there is a lot of physical pressure and there is a lot of photon pressure from X-ray, gamma rays, and all those. Those things can be designed in such a way that you can reflect, compress things before it physically blows apart, and you can achieve boom. So we had normal explosives boom, then we had fission boom. That fission boom triggered a fusion boom, and that was done on 1 November 1952. So this is the first time humanity yielded fusion, like fusion on command became a reality. And then we built fusers. Again, fusers have been worked on. Fusers started to work on 1959. Basically, if you have seen this thing, if you want to do fusion in home, you can do that. The first time humanity cracked that puppy was in 1959. Now, if you have seen like Soviet Union, you must have realized that Soviet Union actually had amazing scientists. Like there is no discussion. Even America knew flat out that Soviet scientists were genuinely good. Thankfully, they had, or unthankfully, depending how you see the history, they had kaput political system. That was just bad. So they had such an advanced understanding of nuclear physics. They came up with the design. They built a tokamak reactor. And if you're like, okay, why everybody is working on tokamak or its variant, it's because of that puppy. That puppy is T4 program variant. Basically, they made T1, T2, T3, and they were achieving everything very quickly. It's like, oh, it works. Okay. Oh, it works. So by T4, they achieved in 1969, basically the time that we landed on the moon, deuterium fusion. Like they achieved it. And they were so confident, they actually brought UK scientists like, bro, come and check. And yeah, it worked. And that is the moment when tokamak became the absolute thing. That's like, people were trying, like, what if we had this? What if we had that? It's like, all of that went out of the window the moment they showed they achieved it. It's not like, we are going to achieve it. No, bro, we achieved it. Now, like, why that is a big deal compared to a fuser? Fuser in principle, like people figured it out, like you can make it. It's a college level project. It's just that it cannot give you energy. In principle, at least that can give. This is like done. This is like on a chemistry level, on an engineering level, this cannot work. As an energy output device, that can work. So everybody switched every other system off and directly went YOLO into tokamak system. Now, you're like, okay, as you can see, like this is the graphite, the actual graphite from CP1 reactor, first nuclear reactor, December 2, 1942, Stagfield, the University of Chicago, a big graphite block. Now here's the deal. That was in 1969. That was long ago. And again, you see, understand the first time we are achieving something that is in 1940s. The reactors are coming online in 1950s. So that's not that far ago. Like first time, oh, this can be done too. Oh, we have a plant that actually works. That was not far ago. Like that was like a child was born. By the time child will go into exceed its teenage year, nuclear is just like a normal thing. Like done, bro. Take it and go home. That's how quickly fission happened. Fusion, even if you start the clock from 1969, it's been 56 years, man. And again, let me be very clear. Can you achieve fusion in your house? Of course, any Tom, Dick, and Harry can do that. School project. And again, all tokamaks can technically do that. Here's the deal. What's the problem then? Well, we haven't achieved break even. So understand this very simply. When you start your engine, you take energy from your battery. You crank the starter motor. Starter motor cranks your engine. Once your engine starts running, it starts to consume fuel, and then it runs an alternator that charges your battery. That's how the system works. So in this, we take energy from the grid, heat that puppy up, do everything that is required to pull vacuum, put heat, do the magnetic currents and all that. We do all that jazz, and then ideally, we're supposed to just start the dumping fuel into it, and that should create enough surplus heat energy that we can run a steam cycle and get enough power that A, we can sell it, and B, still have enough that we can charge the circuit, as in run all the power requirement. So this is what we call break-even factor. Now, we generally need in nuclear fusion case scenario around 200x. Not 1x, not 2x, 200x. And yeah, those things consume power like there is no tomorrow. Like just because there's a superconducting magnet does not mean it's 0 amp. The amps are in kilo amps. It's not even like, oh, 5 amp, 10 amp. Nah. Kilo amps. So bonkers amount of energy is consumed just to achieve fusion. So it has to create so much surplus heat that A, you can run a steam cycle that itself will waste as high as 70% of energy. And then you have to take the 30% output in that. A, sell it. B, have enough of it diversion to run the system. So that's why the break-even factor has to be 200. So this is history. Like, this is old technology. We have been tried, and right now, given the physics and understanding of reality and humanity, I don't think fusion is happening anytime soon. So let's dive deeper into fission part of it. Now, fission works. That is absolutely true. It's real. You can buy it, go YOLO on it. It's real. It's here. It's great. But as a weapon, meaning if you're like, hey, should India build fission nuclear power plants for energy? Hell no. Should India build fission nuclear power plants for its submarine fleet, for its basically aircraft carrier? Shut up, take money. So, of course, it's a weapon technology. Like, okay, then why we are not worried about soldiers with this sort of technology? Well, here's the deal. They already have what we call Brahmastra, aka nuclear boom devices. And we have Triad, as in like airplanes that can boom the planet. We have submarines that can boom the planet. We have airplanes, submarines, land vehicles that can boom the planet. So fundamentally, it's like, it's irrelevant. At that point in time, it's irrelevant. If you have, shift delete the planet button next to your main console, we good, bruh. Like, you can keep a nuclear reactor, it does not matter. Another, the most useful, peaceful part of it is frontier power source. Meaning, if humanity has to go to moon and actually do something useful, like actually lay a foundation of humanity that we can grow from it, yeah, that requires fusion. Fission. There is no discussion about it. Like, it cannot be done if solar alone. Like, it just cannot be. Again, you will use solar for everything, but you will need fission as a what you call base load, as in to make sure heat would be desirable there. So heat, awesome, and having energy during the night time of 15 days. So that's awesome. So it is really good. It's here. It's real. It works. It's an awesome weapons technology. Money is no matter. You do not have to worry about return on investment. So awesome there. And frontier power source, nothing else will work. So that's awesome. Now let's understand certain boom events that happened. So boom event number 1, 3 Mile Island. Now again, as a boom event, there was no boom. There was just oops event. So in that oops event, you had a key that had a giant tag that tagged basically blocked a light that's supposed to warn the operator something went kaput. And you're like, wait a minute. Did we really have America's first nuclear oops by that? Yes. And it's a messy. Like, if you look into the research paper of that, like, what the hell? The reality was, system was so complex, so many variables, so many valves, so many circuits were there. Good luck trying to figure it out. Like, it was, they basically specified, it's not that something bad is going to happen, is that when something bad is going to happen. Because again, it was so messy. Like, you were like, okay, we have this system and that system. Again, all system assumes that everything else is working. So minor failure can become cascade. Now, nothing bad happened here, like no kaboom event, minor meltdown. But again, it had containment building, containment guarding, radiation leakage was negligible. So, but it really bitch slapped the popularity of nukes at that point in time, like flat out. People just like, nope. And again, you had to do evacuation there, assuming the worst case scenario. That really was a big slap against nuclear energy. And it happened in America. Now, here's the deal. That itself was not that bad. Right? In fact, it took them almost a week, and best scientists from everywhere, what the hell is going on? I'm not joking. There was a point where they're like, does it have hydrogen? What the hell will happen with the hydrogen? They were not sure, like, will hydrogen just react back with oxygen? Will it leak out through the material? What will happen? Or will it go boom? What will happen? It was unknown. So this showed the complexity side of it. On paper, fission is just like, do this and done, go home. Reality was like, bro, even hydrogen is confusing here. So that was bitch slap. This was kick in the balls. This is what we call Chernobyl. This happened in 1986. This was bad. This was Soviet engineering and what they call cost-effective engineering, meaning there was no shield. And ironic part is, it would have been better if they did not had pressed that basically shut it down button. Again, it would have melted through. If they had not pressed the shutdown button and, like, started lowering down the rods one by one, it would have melted through. But again, that would have been better compared to going kaboom. So it went to kaboom because of the basically control rod failure design. Like, the design was bad. And again, they did not have content. Like, I have to say, Japanese and American, they built the design in such a way that if reactor goes kaput, the shield building should be able to endure it enough where it's like, okay, containment, some amount of containment. But Russian was like, awesome technology, no bad things will ever happen. So it happened. Now, it created a very big ripple effect because this was so bad, it was being detected without satellites. That's how bad it was. So people are like, okay, we have to solve this. So they created what we call nuclear safety committees and things of that nature, where there are like lot of countries. I mean, India, China, France, every Tom, Dick and Harry, everybody got into it and was like, okay, we're going to have a committee and we're going to go there, check, analyze everything, because this was bad. Like, this was psychologically bad. This was actually bad. So they're like, okay, we have to do better. So they started to do better. Then we had Japanese ego going boom. That happened in Fukushima plant in 2011. Now here's the deal. Why the heck that happened? That should not happen. That's just pure Japanese ego. Here's the ironic part. I'm not even trying to look into it because how true it is or how true it could be. I hope it's false. But the idea is the Nuclear Safety Committee did warn them, you do not have tsunami wall that is high enough. And they're like, we are Japanese. We know how tsunami works. It's like, bro, you know the best case tsunami. You do not know the worst case tsunami. You do not tempt nature. The wall was too shallow. It had to be high. It had to be huge. It had to be like, bitch please to tsunami, and tsunami just bitch please that. Now, what's the penalty with that? Well, here's the nuclear reactors do not like to be turned off. There is no off button in a nuclear reactor. You cannot just like, oh, we're gonna insert control rod, everything is fine. No, it will go kaboom. That's what happened. This is one another complex thing you have to understand. When you put control rods into it, turn it off, all it does, it turns off fission, not a decay bioproducts. The decay products, the daughter products, they are still emitting heat, and it's bonkers amount of heat. If you do not take it away, the best case scenario at that point in time, it can melt through the reactor wall. Worst case scenario, it will go kaboom. So that is one thing. That's why I said turning off reactor, like people say, press the button, reactor off. No. Press the button, turn the reactor off, and make sure there is enough high pressure water, cooling water going into it. And again, it has to be high pressure. It cannot be just like, okay, diesel was like, you are talking megawatt hour kind of power consumption of motors that can pump enough psi of water to go through the reactor. Otherwise, water will be there, it will turn to steam, it will create back pressure, and you will not be able to cool it down. That's what happened here. So tsunami happens because the backup generators were underground. They were on the basement. They're supposed to be in 3 layers: underground, surface, and building top. If they had 3, at least 1 or 2 of them would have been working in tsunami scenario. They did not. They had everything underwater. Under the basement, and it was not even designed as a sealed containment unit. Whereas like, okay, even if the whole area was flooded, it will still work. Tsunami happens. SCADA system triggers. Okay, everything so far works as it should. It's just that now SCADA system is like, okay, bro, cooling water, bro. Cooling water is like, cooling pumps are like, I got this, fam. SCADA system, okay, turn on the power. Okay, grid is offline. Okay, you turn off the power, it is offline. Okay, turn on the backup generator. Yeah, backup generator underwater, no generator, kaboom. This was the first boom event that was captured on camera. Now, let that be very clear. It's not the reactor that went boom, is the cooling pond. And reactor went boom inside, as in like it melted through. It did have catastrophic failure in that reactor design. But thankfully, the container building is like, I got this. And the cooling pond of the spent fuel went kaboom. Yeah, that's also another thing. So at that point in time, this was, oops. This was kick in the ass. This was like, yeah, nuclear is just not human friendly, as in humans make mistake. Let that be very clear. And on paper, all 3 designs were like, this is perfect. Every Tom, Dick and Harry says that like, oh, we have better designs. No, you do not. You have hope and dreams that you have a better design. Same happens in aviation also. People have learned it the hard way that you hope and pray and just try it in real life. There is nothing, oh, we know there will not be any fault. It's like, and then life bitch slaps you. It's like, oh. Only after boom event is like, oh. And I have no idea how many people I've seen where it's like, oh, we can have like, electromagnet that has the control rod. So if anything bad happens, control rod will go down. It explodes after, not before. This would not have happened. If this was a melt-through reactor, basically it melt through inside, it would have been minor inconvenience. Heck, nobody would even known after Soviet Union had fallen. People were like, okay, why this area is a bit radioactive? Then we're like, oh, that's what happened. So first thing, humans cannot make perfect system. Anyone delusional enough to think, oh, we know how this design will work in all conditions? No, you do not. You hope for it. You could have positive feedback. You can have negative feedback. You are just hoping that it works as you wish it to. Nature is like, bitch, please. So, because again, we are not gods, nor time traveler. We do not have the luxury of foresight. It was like, oh, imagine this would have been a minor inconvenience if they put the generator on top, or if they're like, okay, generators are big, heavy, let's just put it on the ground, but seal it so it can survive tsunami, or build the wall, exponentially tall wall, exponentially well sealed generator systems, and multiple generator system in multiple altitude. But no. So that's the whole point. Humans cannot make a perfect system. If you think that, you just cuckoo. Like, oh, we have this design. You hope that it works. Nothing more than that. Now, so far, you might be able to rationalize that. But here's the deal. 2020 did happen. Meaning, solar and wind changed the game. At this point in time, this old design was built on a philosophy of 1970s. Meaning, coal had a price. Nuclear, fossil, fuel, basically fission materials had a price. However, Solar and wind does not have a price, meaning they started and they started to grow. And if you remember news broadcast from 2005 to 2015, there was a talk like, yeah, solar and wind is cool and all, but it's not practical. It cannot scale to feed basically a nation. Right now, we're like, it can easily feed a nation. Like, it's easy. Like, bro, take it and go. Like, it's done. That part is sorted. It's the intermittence that is the issue, and lack of grid inertia that is the issue. But energy part is sorted. And after 2020, the levelized cost of energy is uncomparable. No, this will work for 70 years first. You're hoping that it works, or even 50 years. Let's just go with 50 years. Here's the deal. You cannot ask a loan for this. Why? The interest rate on a solar is much lower compared to interest rate on a nuclear. Why? Assume they are giving you same percentage, because this ROI will start after 10 years. I'm being way too optimistic that you can build start to finish a nuclear reactor in 10 years. Let's assume you did that. Solar can be done in weeks, months. Like India was building it's a giant solar farm at 1 megawatt per day. We are literally adding that much capacity. So by the time you will complete this, the ROI would have been done on a solar farm. You cannot compete in terms of system. And again, wind, damn, I have to say that Europeans are doing some amazing system. They have a system that builds a floating substation, another system that lays down the cable, another system that drills the pylon, another system that assembles the fan. Everything is like automated. It's like, bro, take it and go. Like, by the time this will, okay, the building is starting to do, and it's like, bro, done, power, selling. So ROI is uncomparable, meaning you cannot take out loan for it. Now, thankfully, all this happened in 70s. It created a paradox. Basically, everybody had nuclear fever, and they're like, okay, what if we covered everything with nuclear power plants? Cool, awesome. But how would you make it? Because again, if you overbuilt a nuclear power plant to handle the worst case scenario, it would be so big that it had to be throttled down most of the time, and it will be economically wasteful. It will just not work. ROI will not be there. So nuclear power plants likes to be a base load, meaning it gives, let's say, 1.56 gigawatt. It has to give 1.6 gigawatt the end. You do not want it to throttle up or down. And again, if you watch the Chernobyl show, that's why it was such a big deal. It's like when we have to do emergency testing and all that, yeah, it's difficult. Nuclear does not like to turn down. And again, if everybody else walked around it, they'll be like, okay, you really can't turn it down. So the concept of time shifted was utilized, and pumped hydro was looked again. Pumped hydro is older than the 1920s, but pumped hydro was scaled up to gigawatt hour. The idea was you make a base load, and then during night time you charge the pumped hydro, and daytime during peak hours you drain it. So charge the battery, discharge the system. So pumped hydro, basically gigawatt hour energy storage, became a reality because of those puppies. And again, that solves the same problem with solar and wind. And again, people always forget about biogas. Biogas is enough powerful. And again, we are building so many jet power plants with what we call natural gas. Shift it. So fundamentally, it's a known reality that this does not work. To give you a context how bad humanity is with long-term projects, we have RTGs in Soviet Union that is still at large. Nobody knows where it is. We are just hoping that it is not completely cracked or irradiating a large amount of area. They used RTGs to basically run lighthouses. Good luck with that. And all the waste that has been created with all the plants of China, India, Russia, everything basically, we are just hoping for that. Now, bad one, we have managed it. Like bad one, we have created a HIP protocol. Basically, we heat that puppy up and compress it, bond it with other things. So who is paying for that? Good luck. Like that's how you know the price of that. It's good luck. It's like, okay, actually when this branch of government is paying for this subsidy with this and all that, yeah, that's why LCOE is not comparable. And again, that's only for the bad part. The ugly, basically that's a really bad reactor parts. The sub parts, they're just hoping that people forget about it. Like there was a long battle. It's like, where would you want to store that? Because again, it's not bad enough to justify the expense, and just laying it on the ground is really bad. So just hope that people forget about it, and hope we do not have a news event after a few decades that there is that yellow barrel is now leaking in the water. Happened. So reality is fundamentally, there is no logic of like who will pay for it. Like everyone's just, oh, it's just, we're going to do it and it's going to be done. Okay, who is paying for that? You know the power of solar panels. You know the power of wind farms. You know the power of even pumped hydro. You know the power of hydro plants. You know all the ecosystem. Nuclear, we just forget about it. It's like, let's just ask money from somewhere. It's coming from the same system, or worst case scenario, government has to go under debt and increase inflation. So fundamentally, all the again, humanity even created what we call nuclear power pacemakers. We never had to worry about like, opening people up and like again replacing the battery. But why don't we use it? Nobody figured out how to actually safely dispose it. And this same civilization, you expect them to like handle these things? Yeah, no. So Fundamentally, we are still fighting for the long-term storage. And again, I'm talking about the wastage that has been created by, and this low wastage scenario, thorium reactor, it's 1000 year. There is no country that has 1000 years of continuous experience. It exists for 1000 years. It does not have continuous experience for 1000 years. Now we come to the delusional world of fusion. Now fusion marketing, I have to say, damn, the marketing is good in this puppy. It has convinced the world that somehow it does not have radiation. Even though, if I remember correctly, you studied this in class 10, that it is worse than fission, as in the reactor itself. You have alpha, beta, gamma, and bitch please radiation known as neutron. Now neutron is so bad, so powerful, it makes other things radioactive. Basically, how the heck you think the graphite blocks became radioactive in Chernobyl? Because it was exposed to high neutron flux. Neutron went kabam into the nucleus of the carbon. Carbon became unstable, elevated up to higher energy level. Now it is trying to destabilize itself, like chill down to a lower state, and it became radioactive. Same happens with water. Basically, it goes kaput in the hydrogen nucleus, and then nucleus goes up in one state, and now it starts to become radioactive. Yes, it makes water radioactive. And you see that person vomiting is like, oh, he was exposed to the reactor water. Yeah, reactor water becomes radioactive when you have neutron flux. So how much neutron flux we are talking about? You need some math. 14.1 mega electron volt. Now, how bad or good that is? Normal fission, again, average is 2 mega electron volt. 2 mega electron volt is bad, but it's not that bad. 14 is brutal. How brutal? Here's the, you must have seen this design. You have tokamak design. Okay, what is that tokamak? Tokamak is supposed to be a vacuum insulated puppy where you have a rod. That rod is of plasma rod. Now, the plasma gives off neutrons. Neutron hits the wall, and that wall is supposed to heat up, and then you run a coolant that becomes your working fluid. Cool, awesome. Here's the deal. We could not have found any material that can handle that. Like nothing exists that can handle that. The best material that can instantaneously does not melt is tungsten. And this is what happens to tungsten when exposed to 14 mega electron volt. It gets destroyed. Like the best design is, yeah, we should be able to handle for 2 years of continuous exposure. Best case scenario. And that's why, like, whenever all the tokamak designs were built, the ones they actually started to test is like, yeah, we have to design replacement system day one. That's why they're building a rope-based robotic system. Rope as in, like, you can't have motors there. The radiation is so high that it will kaput itself, even when turned off, because these things have enough residual radiation. So they have a robotics that can go and replace parts every 2 years. And that's optimistic. Let that be clear. Nobody has actually run something for 2 years and be like, okay, this plant, again, this is not looking good. And be mindful, it actually injects nucleus inside the material, like perfectly material, and it's not bubbling. Tungsten is bubbling. How the heck? Okay, it's injecting material into it. So it destroys everything. So anybody's like, oh, we're going to build a reactor. Cool, awesome, GG, I can believe you. How the heck you're maintaining the material? Like, there is no discussion, like, how the heck you're gonna, like, it's gonna be sacrificial material. How the heck you're gonna handle it? At least in the tokamak system, they're like, okay, this is what we're gonna do. They have a robot that can, like, swap out the bottom section. They have a weird robotic arm that goes on, replace on each of the panels. Like, a lot of systems is there. How the heck you're handling that steel? That steel itself will go kaput. Again, I do not expect it kaput in day one, but it will go kaput in 6 months. And it's like, okay, it's aneutronic. No, it's not aneutronic. Only proton-boron reactions are 100% aneutronic. This has 50% neutron. And again, same electron volt. You're going to be kaput. So fundamentally, nothing exists that can withstand that much neutron flux and be like, I got this. We do not have vibranium or uru. And again, 2 years, to give you a context, coal power plants do not shut off in that time frame. Normal nuclear power plants, they're like, bro, we do not touch this for 10 years. Like, just don't touch it. Nuclear submarines, don't touch it. Like, if they can design it right, it will be like, yeah, just during decommissioning, they have to touch it. And I think they refuel it every 10 years. So fundamentally, that's the issue. And we do not know how to achieve stable fusion. Like in fission, we achieved it. Like, okay, we have a fission, we achieved it. Fusion, we have not achieved. We have pulse fusion at best case scenario, which is like, that's all we got. There is no like, it's not fire. We have not reached fusion fire, not yet. So it's not a furnace that works. It's just that's all. It's like, you know, in cold winter you're cranking your diesel engine, is like that's all we got. It just does not work. And again, we need 200x. And now again, why don't we achieve it? Because again, if you have watched any documentary, any scientist, oh, we're gonna make a plasma, it's gonna be hot and it's gonna work. It's like, why the heck it does not work? 60 years is long enough time. Why the heck it does not work? Well, we do not know where the energy is going. That's the reality of it. look into the papers that ITER is publishing. One of the interesting one that was very recent is like, oh, we figured out that is emitting X-rays, because again, you are forcing so much energy there. Atoms do not like that kind of energy. Like the soup is not liking that energy. It has to create some way of dumping that energy. Yeah, that's Bromstrong radiation. Basically the same thing that we use for X-ray. It's dumping X-ray. I'm like, what the hell? How the heck you gonna make sure that it's not cooling the plasma? You can't. You can't stop photons. You can't stop neutron. You're just hoping that a positive charge particle can do most of the work. So that's why it's very difficult. We just do not know. Like nobody can sit down and design a reactor that works, like flat out. If anybody is selling you that, yeah, they're a salesman or a pump and dump scheme. And again, be mindful. We have to achieve 200x. Yeah, that's not. And again, private claims. I'm like, damn. Like we're gonna build this. It's like cool, awesome. Let's assume you achieve like fusion. Let's assume you achieve break even. And again, at break even of 200x, those things will create bonkers amount of flux. At that point in time, your material will not last. Like this thing happened in short run duration. By the way, I think Japan is building a new plant that is solely for high neutron flux research. So like, can we actually build a material that can handle it? Because right now the reality is like, just build a robots that can swap parts very quickly. It's like, it's not looking good. Realistically, it's not looking good. So claims, and again, claims are free. It's like 2028, we're gonna sell power. It's like, no, you're gonna sell cocaine. You're just bullshit. Again, assuming you have Tony Stark in your team and you built this, just by legal procedures and paperwork, you will not be able to do it. Like, that's how I know, like, and so many people lying so much, it really hurts people. And again, you're burning public money. And you're like, no, it's not public, it's privately funded. Do you really think a rich person will risk his own money? Really? So that's the fission part of it. It's just sad. Like, again, take $1 billion and again, $30 billion. It's like, bro, $30 billion is so much. You can put whole of the Sahara with solar panel, put a HVDC connection to other continents and be like, just, bruh, we done. We done, bruh. Now, you have to understand, there is nothing wrong with nuclear, everything wrong with humans. Now, again, you have to handle with like you have to design a system with human in mind. You cannot, oh, we want an alien that is perfectly perfect, that never bad things happen. It's like, no, we are humans, deal with it. Now, what is the reality of humans? We could not handle microplastic, which is tragic given the fact that engineers who built this plastic, they knew for a fact that plastic cannot degrade. That's the whole point. Even ultraviolet only breaks it down, does not disintegrate it. So the idea was create pyrolysis, aka put this plastic puppy into a chamber, pull oxygen out of there and cook it and break it down into liquid. At that point in time, consume that liquid into your refineries so you can have less of the raw crude oil consumption, or burn it directly into compression engines. It works like a diesel. We did not do that. We literally convinced basically dumb people, basically multinational corporations. So like, okay, let's put public, let's teach them to recycle something that is so cheap that it is worthless. Let's recycle that and watch everybody dying of microplastic. That civilization is gonna handle nuclear. What cocaine are you on? Like, who is the supplier, man? Like, I need that supply. And again, we are not in 70s anymore. So this delusion that every scientist, every engineer is like, we're just gonna do this. Like, no, you can't. This whole idea of 24/7 power, again, you don't need 24/7 power if the power that you're getting, that is random, it's hyper cheap. If it is so cheap that you can have energy storage, which again, nuclear is the reason why we have energy storage, you don't have to worry about it. Like, our world has changed basically from 70s when people were dreaming of this. We went from what we call centralized grid to distributed grid, and it's far more robust against war scenario, far more robust against sabotage, far more robust against everything basically. So, and everybody's like, okay, we're gonna build nuclear, it's safe. No, it's not safe against human. You have war, that's a real thing, it happens. Civil war, it happens inside a country. Terrorism, it's a real thing. And nature. And I really let that be very clear. If you ever say that I'm going to build an engineering structure that can handle nature, nature will take it personally. Don't do that. And again, that's Chernobyl, drone attack that happened there. Again, it could be a faulty drone, it could be a faulty system, but you are risking that with your country. When we're like, okay, let's gonna build a nuclear power plant here. And like, we're gonna have a miniature system. Have you seen the cleanup cost? Like, what's the worst can happen if you boom a hydro dam? Bad scenario. How long it will take to come back to reality, normal? 2 years. Done, go home. People will forget about it. How long does it took to recover Chernobyl? How long did it took to control Z Fukushima? Good luck with that. So that's the whole point. Humanity exists. So again, Americans have this idea like nobody can actually attack them. Again, nobody has a very long range capacity. So the war is not a thing. But again, read American history. You have civil war. You are going boom boom with each other. Somebody can decide to go kaboom. And terrorism. You have buildings that went kaput. because of that. So don't tempt fate. That's the whole idea. And waste disposable requires more money that I have not seen any true accounting of that. Like Europe is like, okay, again, France is creating so much of it. It's like, okay, we're going to drill somewhere in like Switzerland or something like that. We're going to drill and like underground this. I'm like, who is paying for that? Like where the money for that is coming from? And you guys are bitching about like, oh, solar panel and wind, which again is the cheapest right now. And again, HVDC, you're gonna need it one way or the another. Pumped hydro, you're gonna need it one way or the another. And again, let's assume somebody figures out magical battery, that problem is solved. And assume you do not have magical batteries. What if you have coal power plants? Oh, you have it. Oh, what if you converted coal into thermal energy storage? Or heck, convert old nuclear into thermal energy storage. So let that be very clear. This idea is like we're going to have a toroid and then we're going to twist that puppy. Then we're going to have stellator and we're going to do this and we're going to do that and we're going to have warm temperature superconductor, which again is an abomination of a line. Say liquid nitrogen superconductor rather than liquid helium, liquid nitrogen. So liquid nitrogen on these things. And people are like, it's so efficient. It's like, have you seen the currents? It's not even in amps, it's in kiloamps. It's like, yeah, can we do this? Of course. Can it create power? No. Can it create power cheap enough? Assuming magical bullshit? No. All the money you put into it, you have to recover it. No. Like right now, humanity has this ick where it's like, what if you just give me one thing to solve all the problems? No. Distribute it. Like how our body works. Other parts of our bodies do other things. Have solar to do some work, wind to do some work, biogas to do some other work, pumped hydro to do some other work, natural gas jet engine power plant to do some other works, coal power plants to do some other work. Like mix all of these together. Right now you can reduce carbon footprint. Or if you think the carbon footprint is not an issue, keep wasting money on this and then die randomly at 600 ppm. I think that's when our crossover point will happen. Right now, when I started as a child, that was 200 to 300. 350 ppm was my like old book that I've seen. Now it's at 400. If we cross 600 ppm, yeah, that time you will know that bad things have happened, because every farmer will, especially if you're from equator band, they will start screaming. It's like, hey, we cannot grow crops because all our crops are dying, even if you are continuously spraying water into it. If that news starts to reach your market, your ears, especially if you are far away from equator, start counting days now. Or you can actually start to solve the problem, or choose. It's up to you. Like choose a civilization that cannot handle plastic. Give it tools that it can handle, not give it nuclear waste like we're gonna do this and that and hope for 10,000 years nothing bad happens. And like people are like, 1,000 years, it's so easy. It's like, there are countable buildings that are 1,000 years old, just countables. And we have thousands of religion, thousands of language. So this was a presentation on like basically what's the reality versus delusion of nuclear. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me your disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.